So the bottom line is we take our critical points, whether they be at zeros as they would be here, or at other points, and we determine whether we have a relative maximum, a relative minimum, or possibly an inflection point that doesn't lead to either. And we do that using the first or second derivative test at each critical point. Now, at a critical point, as we've seen, like this one, our second derivative test would tell us that the graph is concave down at this point, and that therefore this is a relative maximum, meaning that the sign of the polynomial function would not change at this point. It would be negative here, reaching a maximum at 0, but then immediately turning around and going back into the negative numbers. And that would occur if you have an even number of linear factors. For example, an x minus z to the 2n, where z is the x-coordinate of this point. N is a positive whole number, so 2n is going to be a positive even whole number. For example, x minus z squared. That would lead you to essentially parabolic behavior in the immediate vicinity of this point, or near parabolic behavior, because of course you'd have all the other factors, and I don't want to go into all that detail. That's something that you would hopefully understand from a really good pre-calculus course, if this was an x minus z squared, okay, if this was a second order zero. In any case, if that happens, you're going to have this behavior. And if it was a higher even power, it would look very similar. It would just be a little bit flatter toward this point. And of course, if you have a real high even power, it could be very flat in the neighborhood of this point. But the only point at which it would hit the axis would be at the zero itself. Now, in the case of a zero where you have a critical point and also an inflection point, then you're going to go on through that zero, but you're going to level off before you do. And that would typically happen if you have, for example, a cube, an x minus z cubed, where z again is the zero, not the same as this one, but that would lead to the behavior very similar to a x cubed power function, a multiple of an x cubed function at this point. And locally it would behave very much like an x cubed function. We understand the x cubed graph would have this sort of characteristic. And of course the linear factors, if it's 2 to the n plus 1, where n is, again, a positive whole number, or a counting number if we want to talk about it that way, then 2n plus 1 is going to be an odd number, and we're going to have an x minus z to an odd numbered power. 3 would be an example of an odd numbered power. Higher odd numbers, 5, 7, 9, and so forth, would just lead to flatter behavior at this point, but would still look very much like what I've sketched here. Then again, at critical points that don't occur at zeros, you have the kind of behavior we're used to seeing. Again, if it's your second derivative is positive, you have concave upward, which means you'd have a minimum. Alternatively, your first derivative goes from negative to 0 to positive. That would, by the first derivative test, indicate a minimum at this point. Similarly, you could get a maximum at this point, relative maximum at this point. And if you had an inflection point that wasn't a 0, then you wouldn't have either a relative maximum or a relative minimum. I think I maybe neglected to discuss this part of the note on the board. And all we're saying here is that your number sign changes can't be greater than your number of zeros. Remember that the sign can only change at a 0, but the sign doesn't necessarily change at a 0. So that it's possible that you would have a sign change for every 0, like so. But as in this case, not necessarily. You don't necessarily change the sign at the 0. And also that the number of zeros can't be greater than the degree of the polynomial. Why is that? Because a 0 can occur only at a linear factor. And the number of linear factors can't exceed the degree. If we go back to this example of a polynomial, you can't have more than 9 linear factors, because if you did, when you multiplied out those linear factors, you would end up with greater than a 9th power. Clearly not possible in this case, and for any polynomial, the number of linear factors can't exceed the power of the highest power that you have in the polynomial function, so that the number of zeros can't exceed the number of degrees. It can be less than the number of degrees. It can be less than the degree. If you have irreducible quadratic factors, they add to the degree of the polynomial without producing zeros. So it's kind of important to understand this set of inequalities. Again, in order to have a sign change, it has to be to 0, but if it's a 0, it doesn't necessarily give you a sign change. And the only zeros can occur at linear factors of the polynomial, and the number of zeros can be less than or equal, must be less than or equal to the degree, because the number of zeros can't exceed the degree, because every zero corresponds to a linear factor, but it can be less than the degree, because you can have irreducible quadratic factors or repeated factors. So that's kind of an extensive summary of something that could probably have been summarized in much fewer words, but people were not understanding this well at all, and I'm not sure this is going to help a lot. Earlier discussions will probably be more helpful. If you don't understand this, it really means you need to go back to earlier discussions and understand the details of how critical points and zeros occur and how they behave.